just to kind of recap where we left off last time. So this unit, we're talking about entropy. And at the end of class last time, we started talking about what happens for truly incompressible substances and for ideal gases. And so we did this kind of side-by-side derivation to see what these relationships look like for an ideal gas. And we came up with two relationships that connect entropy difference to CV, so the heat capacity with the volume held constant, and another relationship with CP. So if you are given information about temperature and specific volume, you can use the equation on the left. And then if you have information about temperature and pressure, you can use the equation on the right. And these two equations are both equivalent, so it doesn't matter which one you use, you should get the same answer. All right, so we're going to kick things off today with an example. All right, and so in this example, we want to determine the change in specific entropy of air undergoing a process from a temperature of 300 K and a pressure of 1 bar to a temperature of 400 K and 5 bar of pressure. Okay, so we have state 1. We have T1 is 300 K and P1 is 1 bar, which is I'm just going to leave this for now. And then state 2, we have T2 is 400 K and P2 is 5 bar. Okay, so what we want to find is our change in specific entropy. So we want to know S2, sorry, lowercase s2 minus S1. Okay. All right. So which equation do you suggest that we use? Does anybody have any feeling on which one we should use? The one on the right, right? So we're given pressure and temperature, so we should use the one on the right. So let's do that. So we will use S2 minus S1 is equal to CP, natural log of the temperature difference, minus R times the natural log of the pressure difference. Okay. So we're going to use this. So for CP, that's the only thing that's missing here. So we need to find CP. All right. So we are going to we can do one of two things. So we can either use the average specific heat, or we could take the CP at T2 plus CP at T1 and then divide this thing by 2. All right, so we can do that, or we can use the average temperature. To find CP. So essentially, I'm going to look up CP at T1 plus T2 divided by 2. All right, and we'll use the tables for that. Okay, but what I am stating kind of, if you read between the lines here, is we're going to assume constant specific heat. So since our temperature difference is 100 K, that's a reasonable enough difference in temperature that we can assume that CP is not going to change dramatically. All right, so we'll use constant specific heat, and then we can either calculate it using one of these two methods. Okay, and we'll use that from, both of these will come from table A2. which is not there. Does anybody have table A2 handy? If not, that's okay. I thought I put it in the notes someplace.
Put it at the very end there. Very end of the whole package.
Is it? I feel like the tables moved around. Oh, I went past it. Okay, this guy, right? Okay, so we are looking for CP, and actually I'm going to copy this and put it with that other problem. Sorry. All right. So we have our CPs. So let's do the following. So our CP at a temperature T1, which is 300 K, is 1.005. And then CP at T2, which is 400 K, is 1.013. So we can put these together and say that CP for this problem is the average between these two. Which is 1.008. Oops. I think, sorry, I'm doing this in my head. So this is kilojoules per kilogram K. All right, or we could have looked up the average temperature between 300 and 400 is just 350, right? And there's also a line item for 350, oops, which would be 1.008, okay? So we can use either of these methods, all right? And I'm just gonna plug this back into our equation. So we have S2 minus S1 is equal to 1.008 kilojoules per kilogram K times the natural log of our second temperature divided by our first temperature. And make sure you're using absolute scale here. So since it's already given to us in Kelvin, we don't have to change anything. Minus R, which is our ideal gas coefficient. So we have 0.287 kilojoules per kilogram K. And the natural log of our pressure ratio, which is 5 bar to 1 bar. All right. Since we're doing a ratio of pressures, the units don't matter as long as the numerator and denominator are the same, right? And we get minus 0.1719 kilojoules per kilogram K. Okay. All right, so hopefully that one felt pretty straightforward. The biggest thing that we had to do was figure out the heat capacity and then choose the appropriate equation. If you went with the equation on the left-hand side here, we could always use the ideal gas law to go from pressure to specific volume, and it would work in just the same way. It would just take a couple of extra steps. Okay. I don't know why I have so many, I don't know what happened in the notes. There's a lot of extra pages, so if you need extra pages later, there they are. Okay. So in most cases, the assumption of constant specific heat might not yield very accurate results. So we should use the ideal gas tables instead in circumstances like that. So if you're looking at the CP table by temperature and the CP values are changing a lot between the two temperatures that you have, then you should use something different like the tables. However, unlike internal energy and enthalpy, entropy doesn't depend on temperature only. So it looks like, if you remember, we have S2 minus S1 is equal to the integral between T1 and T2 of Cp, which is a function of temperature, over T dt, minus R times the natural log of the pressure ratios, or the pressure ratio. And for an incompressible gas, we have that entropy is a function of temperature and pressure, or we can write this as a function of temperature and specific volume. Okay. So the air tables list a quantity that is called the standard state entropy. So it's denoted as S with a subscript 0, and it's a function of temperature. So this is the standard state entropy. And it represents the specific entropy at a state where the temperature and the pressure is, the temperature is T and the pressure is 1 atmosphere relative to a reference value at a temperature of 0 Kelvin and 1 atmosphere. Okay, so it is defined like this. So it's S0 of T is equal to the integral from 0 to T of Cp of T divided by T dt. Okay, so if we remember the chain rule of integration, which says if we have an integral from a to b of f of x dx, we can break this up as an integral. Oh, sorry. If we have the integral from a to b of f of x plus the integral from b to c of f of x dx, we can write this exactly the same as just integrating straight from a to c, right? All right, so I'm gonna rearrange this and say, if we really want to know the integral from b to c of f of x, then that is just our integral from a to c of f of x minus our integral from a to b of f of x. Okay. So this probably looks kind of random that I've brought this up. The reason is because we can think of this as T1 is our B and T2 is our C. So if we want to know T2, an integral from T1 to T2, we now need to use this arbitrary spot A, and we're going to use that as our absolute value, or our absolute zero temperature. So we're going to let this be our T equals 0K. Okay, so this is where this S0 is going to be useful to us. All right, so we can rewrite our entropy equation in the following way. So since we had S2 minus S1 is equal to the integral from T1 to T2 of Cp, which is a function of T divided by T dt, minus R natural log of P2 divided by P1, we can rewrite this as the following. So we can say that the integral from T1 to T2 of Cp T over T dt is equal to an integral from 0 to T2 Cp T over T dt minus integral from 0 to T1 Cp of T over T dt, where this first term is the exact definition of this S0 value evaluated at T2. And then our second term here is S0 evaluated at T1. So this is S0 at T1. Okay, so if we actually want to include the dependence of Cp on temperature, we can use these standard entropy values at our two temperatures and take that into account entirely. Does that make sense? Sort of the calculus gymnastics that we did there. Okay, great. So putting that back together, if we're using the air tables, our difference in entropy is going to look like the following. So we have S1 minus S2 is equal to, and I'm going to substitute for this term this expression. Okay. So we have S0 evaluated at T2 minus S0 evaluated at T1. And then we keep our minus R times natural log of P2 over P1. All right. So this is for using air tables and assuming non-constant Cp. Okay, does that make sense? Okay. So as a note here, S0 values can be found in tables A21 or A21E if you need English units. Okay? So a big caveat here is remember that these S0 values are not total specific entropy. All right, so if we look at this equation right here, if we want to get total specific entropy, we also have to take off this log of the pressure ratio term, okay? So just be careful because it feels tempting because it's an S, but it's not the whole story, okay? Yeah,
The problem, like on the exam, will you say like we can't assume the constant specific?
yeah, I would be specific about it, whether you can or not. Other questions? Okay, let's do an example then. All right. Okay, so we want to determine in this example the specific entropy of air undergoing a process that begins at a state where the temperature is 300 Kelvin and the pressure is 100 kilopascals to a state where the temperature is 1000 Kelvin and the pressure is 300 kPa. All right, so we have our state one is T1 is 300K and P1 is 100 kPa. And then state two is T2 is equal to 1000 K and P2 is 300 kPa. All right, and we want to find S2 minus S1. Right? So we are going to notice that the change in temperature is quite large here. So we're changing 700 Kelvin. So we're going to assume that CP cannot be considered a constant with respect to temperature, just because that's a really huge temperature swing. So we're going to use the equation that we just developed using the air tables. So we will use, since delta T is very large, CP is a constant is not a good assumption. So instead, we're going to use the following. So we're going to use S2 minus S1 is equal to S0 at T2 minus S0 at T1 minus R times the natural log of the ratio of pressures. Okay. Okay, so we are going to, we know our pressure ratios and we know R, of course. We need to find these. So we're going to find these two things from table A21, which I think, yes, finally is right here. Okay, so all we're going to do is we are looking for data from this column. So it's just S with a subscript 0. All right, and we're going to look it up by temperature. So for our first one, we're looking for S0 at T2, which is 1000 Kelvin. So we're going to go over to 1000 Kelvin, which is this row right here. And we're looking at our last value. So we have 2.96770. You guys have ruined me. I just want you to know. It's in the table. Now I know to look for the reaction. I saw it. Okay. Okay, so now I don't even know where I'm at. All right, so I have, I'm not gonna say it again. This number. What? I know, I thought it in my head. All right, kilojoules per kilogram K. And then, so help me, let's find the one at T1. So T1 is 300. So we'll go to our line for 300. All right, so we have 1.70203. Again, kilojoules per kilogram K. All right, and now I'm just going to do this arithmetic. All right, so I have S2 minus S1 is equal to 2.96770 kilojoules per kilogram K minus 1.70203 kilojoules per kilogram K minus R, which is our ideal gas constant, which is 0.287 kilojoules per kilogram K. And then we have natural log of our pressure difference. So our pressure difference is 300 kPa over 100 kPa, which gives us 0.9504 kilojoules per kilogram K. Okay, any questions on using this form of the equation? No? Is it good? Okay, great. Okay. All right, so now we're going to talk about isentropic processes involving ideal gases. So remember that if we have an isentropic process, that means that our entropy is going to stay the same. So we have S1 is equal to S2. So this is just the definition of an isentropic process. And actually, for your equation sheets, I would highly recommend writing down the meanings of adiabatic, isentropic, isothermal, and adiabatic, and isobaric, and isochoric. Those ones. I think those are all of them. Or commit it to memory, even better yet. Okay, so we want to determine relationships between pressure. I'm just going to write this as P, specific volume, and temperature. All right, and so since the values of specific entry are not tabulated for ideal gases, we need to develop a special procedure to handle this type of process. All right, and so that's what we're going to do now. So we are going to assume constant specific heat. And I'm going to give you two derivations side by side again, because it was so fun the first time, right? And I'll try to write small. I think I can fit it in here. Hopefully. I'm going to move this though to like right here. Okay, so we're going to do two derivations side by side because we have those two versions of our entropy difference from before. So that's what I'm going to start with. So on this side, we're going to consider if we have temperature difference and specific volume change. So we would use this form of the equation. So we have entropy difference is CV times the natural log of T2 divided by T1 plus R natural log of the ratio of specific volumes. All right, and then if we're given pressure instead of specific volume, we'll use this one. So we have CP, natural log of the temperature difference, minus R times natural log of the pressure ratio. Okay. So if we have an isentropic process, that means that S2 and S1 are equal. So our left-hand side for both of these is 0, right? So isentropic S2 equals S1. So left-hand side is 0 for both of these. So that means that I have 0 is equal to CV natural log of T2 over T1 plus R natural log of V2 over V1. And a similar thing over here. So I have 0 is CP times the natural log of T2 over T1 minus R natural log of P2 over P1. Okay. I am going to move one term to the other side of this equation. So I just have an equality to look at. So I have the following. So I have natural log of T2 over T1 is equal to minus R divided by CV natural log of V2 over V1. And similarly over here, so I have natural log of T2 over T1 is equal to R over CP natural log of P2 over P1. Okay, I am going to do a process with natural logs that will get rid of this negative sign in front of my left-hand side equation. So if you remember, the natural log of 1 over x is equal to the negative natural log of x. All right. So, or another way of writing, actually, I don't like that. Hang on. My brain works better this way. So what I'm going to do is I'm going to say, if I have some coefficient, natural log of x, this is equal to natural log of x raised to a. Okay, so all I'm going to do is I'm going to take this -1 out front and make it a power inside of the natural log. So I have natural log of v2 over v1 to the -1. That just flips the numerator and denominator around. All right, so I have natural log of t2 over t1 is equal to r over cv, natural log of v1 over v2. And so I'm using this rule to go from here to here. Is everybody cozy with that? That's fine? Okay, great. All right. And I'm going to also use that rule again. And I'm going to take the r over cv and the r over cp, and I'm going to make that the power inside of my natural log. Okay, so I can use that rule again to say that natural log of t2 over t1 is equal to the natural log of v1 over v2 raised to the power r over cv. And then same thing over here. So I have natural log of t2 over t1 is equal to natural log of p2 over p1 raised to the power r over cp. Okay. Okay, so now I'm going to give you a comment that's kind of a reminder, but maybe something new. So for an ideal gas, Cp minus Cv is equal to R, which means that R over Cv is just Cp minus Cv over Cv. And there is a special parameter called K, which is the specific heat ratio. And that is just the ratio of Cp to Cv. So it's just Cp divided by Cv. Have I said this in class already? K? Have we seen K yet? Okay. So in this expression, this is K, right? So it turns out that we can rewrite this exponent as K minus 1. And we can rewrite this expression, or this exponent, as K minus 1 divided by K. Okay? So that means that I have the following. So I'm gonna exponentiate both sides to get rid of the logs. Since I have a log on both sides, I can do that. And get the following. So exponentiate both sides. And that gives us T2 over T1 is equal to V1 over V2 raised to the power K minus 1. And then I also have T2 over T1 is equal to P2 over P1 raised to the power K minus 1 divided by K. Okay, so these are very handy relationships to use. And if any of you are ME students and you take intermediate fluid mechanics with me, which is an elective, these will come up again when we talk about compressible flows. So everything will come full circle if you take that class. But just to remind you, these both only apply for an isentropic process with an ideal gas and constant specific heat. Okay, so for both of these, isentropic, ideal gas, constant CP or CV. Okay. You can also combine these expressions to get the following. So you can get P2 over P1 is equal to V1 over V2 raised to the K power, or P1 V1 raised to the K is equal to P2 V2 raised to the K. And note that K can be looked up in table A2. So table A2 was where we were looking up CP and CV. So the ratio of those two things is also in that table. And it is K. All right, so we figured out that kind of follow-up relationship by just noticing that the left-hand side equation and the right-hand side equation both are T2 over T1 on the left-hand side. So you can just set them equal to each other and you get those. And so to bring things back to something we talked about, I think in topic 2, there's something kind of interesting that we can observe here. So this means that an isentropic process with an ideal gas and constant specific heat is a polytropic process. Remember that? Everything's coming together, right? Because polytropic process means that P times V raised to some power is a constant. Sorry, we called it N before. So this is for a polytropic process in general. So in an isentropic process with an ideal gas and constant specific heat, it's a polytropic process where N is equal to K. Cool, right? All right. Any questions on kind of that flow of derivation or the resulting equations or anything like that? Okay. Okay, let's do an example. This is a very short one. That's why I've only given you a tiny bit of space. Okay, so in this one, we have air is expanding isentropically. So we're gonna wanna, when we're doing these problems, we're gonna wanna kind of look out for some key words that will help us decide which relationships to use, so which equations to use. So we're expanding isentropically from a pressure of 600 kPa and a temperature of 1100 Kelvin to a temperature of 700 Kelvin. We want to determine the final pressure, assuming constant specific heat. Okay, so we're also given that we're going to make this assumption. And we're also told that it's air, which is an ideal gas. So we have all of our assumptions from that last derivation kind of ticked off here. So we have an isentropic process, we have an ideal gas, and we have constant specific heat. So that means that we can use the relationship T2 over T1 is equal to P2 over P1, K minus 1 divided by K. All right, and I'm using this one because we're given pressures and temperatures, and we're looking for a pressure, right? Okay. So, we want to find P2, right? And we have T2, we have T1, we have not P2, we have P1, and then we can look up K in the table. All right, so we will use, so for K, we're gonna use the value at T average. So this is just T1 plus T2 divided by 2, which in this case, we have 1100 plus 700 divided by 2. So we're going to use 900 Kelvin. And when we look that up, which it might be, let me see. No, maybe not. Okay, so this value in the tables, I thought I had it in here, but it's the same one that has the CP and CV listed on it by temperature. We get 1.344. All right. And we are going to solve this equation for P2. Is everybody comfortable with how we do that? I'll show you just in case. It's not long. Okay, so I am going to move my exponent over to the other side, which looks like this. So I am going to raise both sides to the power K over K minus 1. And the reason that I'm doing that is because if I multiply, or if I have the power K minus 1 over K and then raise that to the power K over K minus 1, this just works out to be power 1, right? Okay. So this is just power 1. All right, so, oops. This means that we have P2 is equal to P1 times T2 over T1 time raised to the power K over K minus 1. All right, so P2 is then equal to 600 kPa times 700 Kelvin over 1100 Kelvin raised to 1.344 divided by 0.344, which gives us 1026 kPa. All right, so again, just make sure your temperatures are absolute here. Any questions on the use of that equation? It's not too bad. All right, cool. Okay, so we can also use ideal gas tables. So again, using the tables is a more accurate approach rather than using a K value from the average temperature. And so to do this, we're going to remember that we had this equation from before where S2 minus S1 is equal to S0 at T2 minus S0 evaluated at T1 minus the ideal gas constant times the log of P2 over P1, right? So remember, these two things are found in the table. So for air, find these in table A21. All right. If we have an isentropic process, the left-hand side is equal to 0, right? So we have 0 is equal to S0 at T2 minus S0 at T1 minus R times the natural log of P2 divided by P1. So if we solve this for the pressure ratio, we can write this as, I'm going to do this in a couple of steps. So I'm going to move my R times the natural log of the pressure ratio over to the left-hand side. So I have R natural log of P2 over P1 is equal to the difference between S0 at T2 minus S0 at T1. All right, then I'm going to divide my both sides by R. So I have natural log of P2 over P1 is equal to S0 at T2 minus S0 at T1 divided by R. And then I'm going to exponentiate both sides. So I have P2 over P1 is equal to the exponential of this fraction, S0 at T2 minus S0 at T1 divided by R. And I can write this slightly differently if I want. So I can also write this as the exponential of S0 at T2 divided by R divided by the exponential of S0 at T1 divided by R. So it turns out that both the numerator and denominator are both of this form. So exponential of some S0 at a temperature divided by R. So this general form depends only on temperature. And it's given a special symbol. So it's denoted as the following. So it's denoted as P with a subscript R. And these are listed in the air tables as well. So this is listed in the air tables. So A21. All right, so we have that PR at some T is equal to the exponential of S0 at T divided by R. All right, and this has no units. Okay, so we can write for an isentropic process with air, we can write that P2 over P1 is equal to PR at T2 divided by PR at T1, or sometimes this is written as PR2 divided by PR1. I can't remember who it was, but somebody was in my office asking about homework. And the question came up, what is the PR in the air tables? I told you to ignore it. Now you don't have to ignore it anymore. Okay. So I will highlight this. So this is a key result that is useful. So to talk a little bit more about PR, so this function PR is sometimes called the relative pressure. Which is honestly kind of a misleading name since it's not a pressure at all. So just be aware of that, but also be careful not to confuse PR with the reduced pressure. Which was called P subscript capital R. And that was in the compressibility chart in topic 3, I believe. Okay. So given the context of the problem, I don't think you're gonna actually be confusing these two things, but I just wanted to make you aware of kind of the slipperiness of the notation here with these two things. Okay, table A21 lists another quantity, VR, sometimes called the relative volume. Again, just like relative pressure, it's not actually a volume, so it's similarly defined. So this is VR at T is equal to RT divided by PR at T. All right, so we're going to use this for isentropic processes using the following relationship. So this means that we can find the ratio of specific volumes for a process between 1 and 2 as VR at T2 divided by VR at T1 or VR2 divided by VR1. Okay, so this again is also only for isentropic processes involving air. Okay. So let's do another example. So if we have air compressed in a car engine from 22 degrees Celsius and 95 kPa in a reversible adiabatic manner, if the compression ratio is 8, determine the final temperature of the air and assume that it is an ideal gas. Okay, so we have a few things that are important to note in here. So we have our ideal gas assumption, which is good. We're also given that the process is reversible and adiabatic. All right. And we have a few other things given to us. So T1 is 22 degrees C and P1 is 95 kPa. Our compression ratio is 8. So compression ratio equals 8 is the same thing as saying our specific volume ratio. So V2 to V1 is 8. Okay. All right. So before we start, I want to talk a little bit more about this reversible adiabatic process. So I'm going to start with our equation that for the entropy balance. So we have our total entropy at 2 minus our total entropy at 1 is equal to the integral from 1 to 2 of delta Q over T plus S gen. All right, so if our process is reversible, that means S gen is 0, right? Oh, reversible. There we go. And if the process is adiabatic, that means that Q is 0. So our entire right-hand side of this equation is 0. So what else can we say about this process then?
S2 is equal to S1.
Wait, say again?
S2 is equal to S1.
Right. And then what special name does that have? Yeah, so this is isentropic. Okay, so we have air. We have isentropic. So we can use these expressions that we just derived. And we are looking for temperature. All right, so what we're going to do is we want to solve for either PR2 or VR2, and we're going to use the tables to interpolate for the temperature because those quantities only depend on temperature. So the strategy is the following. Since PR and VR depend only on temperature, if we find either PR2 or VR2, then we can find T. Right? Does that make sense? So we're going to do some degree of interpolation probably. All right. Okay. So let's use, since we're given our compression ratio, I would suggest that we use the VR equation. So we're going to use that V2 over V1 is equal to R2 over VR1. All right, and we want to find VR2, so I'm going to solve this for VR2. So I have VR2 is equal to VR1 times V2 over V1. And this is 8. So I'm going to put 8 in here. All right. And we're given the temperature for T1, so we can find VR1. All right. So we're going to use T1 equals 22 degrees C. All right, and the tables are in Kelvin, so we need to convert this. So T1 is equal to 22C plus 273, and this will give us Kelvin. So we have 295 Kelvin, right? All right, so do I have the table that I need? No, I don't. Is it not in here anywhere? It's before that? Where? Wait, do you know what it is? It's where?
It's here, right?
Yeah. This is air. But like, what page is it on? Oh, here. Okay, thank you. Okay, so we're looking at 295, right? Is that what I said? Okay, 295. And then here is our VR column. So we have 647.9. So I will, you know what? Hang on. I'm just going to take a little screen grab of this. All right. Okay, so we have VR1 is equal to 647.9 kilojoules per kilogram K. All right, so this means that VR2 is equal to 8 times 647.9 kilojoules per kilogram K. All right, which is 80 80.9. Oh, sorry. I made a mistake. So V, the compression ratio I wrote wrong. So this is V1 over V2. Sorry. So V1 over V2 is 8. So that means V2 over V1 is 1 over 8, right? Sorry about that. So this is 1 divided by 8. Okay. And then this is 1 divided by 8. Okay. Sorry about that. Okay. So we have 80.99 kilojoules per kilogram K. Or no, I'm sorry. These don't have units. Goodness me. Okay. All right. So now we want to find T2. So we need to interpolate. All right. So can anybody tell me some VRs that are close to 80.99 and let me know their temperatures?
81.89. The temperature of 660.
Okay.
78.61. The temperature of 670.
Wait, 78 point, what was it? 78.61. And then what was the temperature?
670.
Okay. All right. So let's do this interpolation to find T2. So interpolate. So I have T2 minus 670 divided by 660 minus 670. I should have put the K on the outside here. And this is equal to 80.99 minus 78.61 divided by 81.89 minus 78.61. All right, and when we solve this equation, we get that T2 is 662.7 Kelvin. Any questions on that one? Okay. Okay, so now let's talk about enthalpy change for an isentropic process. So if we have an isentropic process, which I will remind you once more, means that S1 equals S2 equals constant. All right. We want to determine an expression for the enthalpy change during such a process. So we're going to start with the TDS relationship. So we have TDS is equal to DH minus VDP. Since entropy is constant, the differential change in entropy is going to be 0. So this is 0 since S is constant. All right. So that means that we can reduce this equation to be 0 is equal to DH minus VP. Oh, DP. I'm sorry. This is DP. All right. And I can just rewrite this as DH is equal to VDP. All right. So I can integrate both sides to find H2 minus H1. So if I integrate from state 1 to state 2, DH is equal to the integral from 1 to 2 VDP. Then this means I have H2 minus H1 is equal to the integral from 1 to 2 of VDP. Oh my gosh. DP. Okay, sorry about that. All right, so we need to figure out how V depends on P in order to do that integral on the right-hand side, right? So we need to know v as a function of p to do this integral. All right. This expression applies to all pure substances. But we still need to know how a specific volume changes with respect to pressure. We know this for one special case though. So in the special case of an incompressible substance, we know that the specific volume is going to be approximately a constant, right? So if it's incompressible, you can apply all the pressure you want to it and the specific volume is not going to change because it does not compress, okay? So that means that we have H2 minus H1 is equal to the specific volume times the integral of dp from 1 to 2, right? So since v is a constant, we can pull it out of the integral, and then we just get v times p2 minus p1. All right, so this is our relationship for an isentropic incompressible substance. Okay. So this is especially useful for analyzing isentropic pumps. All right, so pumps are always going to have an incompressible substance because they always have liquids and we generally assume liquids are incompressible. Okay. Okay, so that kind of leads us into our last section for this unit, which is isentropic efficiencies for steady flow devices. All right, so we know that irreversibilities are going to degrade the performance of devices that we want to work with. So we'd like to be able to express. No, stop. The room's decided. They're like, no, enough. Come on. What did I do? I don't understand. Did I like visibly push a button? The thermo ghosts in the room were like, I've had enough. No more. Okay. Um, so we want to express the degree of degradation in performance due to irreversibilities in a quantitative way by defining efficiencies for steady flow devices. So these should compare to the actual performance of the device compared to an idealized model. Okay, so what would be a good ideal device model? All right. So we have, when we're talking about real systems, we have heat transfer between devices like turbines, compressors, and all those things. So like heat transfer to ambient is unavoidable, but they're designed to operate under adiabatic conditions. So we should design our ideal device as adiabatic too. All right, so we're gonna make it adiabatic. And since we want to characterize kind of the ideal model, we should also make our device reversible. All right. So when we combine these two things together, which we just did for a previous example, which is right here. Anytime you have a system or a process that is adiabatic and reversible, it must also be isentropic. Okay, so we're also saying that this is isentropic. Okay. Okay. So that means that if we compare our actual device versus our ideal device, what we have is, here's our device. We have the same inputs or same inlets. So we have PI, TI, HI, SI, and M dot. And they are going to stay the same. And M dot. Okay, so these are equivalent. For both. All right, and then the outlets are what are going to be different. So our exit conditions, we are going to have pressure at the exit, which is going to be the same between both, but then we're going to have some differences. So for our actual device, we will have TE, HE, and SE, so temperature, enthalpy, and entropy. And then for our ideal device, we will have TE, S, TH, oh no, HES, and then SES, which is the same as SI. All right, because we are assuming isentropic. And you might be wondering to yourself, why the subscript S? Should it not be I or something for ideal? The reason for this is the subscript S indicates constant entropy. Okay, so subscript S is for constant entropy or isentropic process. Okay. Okay, so the efficiencies that we are going to define for different devices are going to be called isentropic efficiencies. So we will define isentropic efficiencies. And they're going to be defined differently depending on what the device we're looking at is. So the first one we're going to look at is isentropic turbine efficiency, which is defined as the following. So we will have the following. So I'm kind of going to repeat that picture that we had before, but for the specific case of a turbine. So this is our turbine. So both of these will have work output. So I'm going to use a subscript A for actual, and then the subscript S for our constant entropy. So this is our actual. This is our ideal. Okay. We still have the same inlet conditions. So we have PI, TI, HI, SI, and M dot. These are the same inlet conditions for both devices. All right, but then the outlets are going to be different. So for the outlet, we have PE, TE, HE, SE. And then for our ideal device, we also have the same exit pressure, but now we have an isentropic exit temperature, an isentropic exit enthalpy, and then an isentropic exit entropy, which is just the same as the inlet entropy. That was really hard to say. Just so you know. Okay. All right. So if we neglect changes in kinetic and potential energy, we're going to assume the turbine's adiabatic, which we already said kind of at the beginning of this, and that it's steady state. Then we can reduce our energy equation to the following. So our energy equation, assuming steady flow, adiabatic, what else did I say? Oh, and neglecting kinetic energy change and potential energy change becomes the following. So we have for our actual, we have W dot of our CV is equal to just WA. So our output work, which is equal to M dot HI minus HE. And then our ideal equation is W dot for our isentropic process is equal to M dot HI minus H exit for an isentropic process. Okay, so we would like to know how W dot A compares to W dot S. All right. And so to do this, we're going to consider the entropy balance for the actual turbine. Okay, so we're going to look at entropy balance for the actual device, which is given by the following. So our time rate of change of the total entropy in the control volume is equal to the sum over all the boundary temperatures that we might have of Q dot over T for each of those boundary temperatures plus M dot times SI minus SE plus the entropy generation for the system. Okay, this is steady, right? So I can get rid of the time derivative term. It's also adiabatic, so I can get rid of the Q dot term. And so I have here that M dot times the difference in entropy between the exit and the inlet is equal to S dot gen, which is greater than or equal to 0, right? So this implies that we must have a circumstance where SE is greater than or equal to SI. They would only be equivalent if it was reversible and S dot gen was 0, right? Okay, so this tells us that the entropy of the fluid increases as it goes through the turbine. All right. And that means that if we look at a HS diagram, the Mollier diagram, which I will reproduce for you here. So our diagram for HS, I'm sketching this, but you would see the curve in the actual diagram. So our enthalpy versus entropy looks like this. So this is a constant pressure line. So these are isobars at PI greater than PE and then PE. All right, so this is our state I, so this is our inlet state, and then this is our exit state. If we want to draw our isentropic exit state, remember that our exit pressure stays the same, so we need to stay on that isobar, but we're going to do it in an isentropic way, so we need to go straight down and not change the entropy value. So this is ES. Okay, so this path here is our actual process. And then this path here is our ideal process. Okay. So if we look at where the entropy values are, so this over here represents HE. So this is our actual exit entropy. And then over here is HES. So this is our isentropic entropy at the exit. All right, so this means that exit enthalpy, which is H, is higher or larger for the actual device compared to the ideal device. Okay. And what that means then is that W dot actual is always going to be less than or equal to W dot for our idealized system, which hopefully makes sense, right? So our idealized system should be outputting more work than our actual system, right? But this is the reason for why. All right. Okay. So we can define our efficiency value as the following. So efficiency is going to be given as eta for a turbine is equal to the actual power output divided by the ideal power output. So this is just W dot A over W dot S. All right, this is always going to be less than or equal to 1, right? So for reference, large turbines typically have efficiencies between 85 and 90%. And then small turbines, bless you, have efficiencies generally below 70%.